math at the end to tell you how you can tell what's the difference in time, like percentage wise, between the guy in the spaceship and the guy that's stationary on Earth. And this over here on the right hand side here, you can see I'm pointing to it. That's the formula. T prime, where you can think of that prime as I. You know what I mean? Like me, I. The T without the prime, that's the spaceship guy. So his, and we were going 80% the speed of light, or 4/5, right? So we said put the 4 in there, the 5 in there, 4/5, right? Square them up, 6. Plug that into your calculator again, and you got 3/5. Every 100 minutes that the Earth person would have, all right, the guy on the spaceship, right, would only get 60% of that. So 100 minutes for Earth, 60 minutes for the traveling space guy, okay? I want you to think of this new concept that things don't happen at the same time for everyone in the universe. Simultaneousness is something that is also about frame of references, okay? I want you to look at this first one right there. See that? CT prime. T is obviously I, you know what I mean? XI, that's my spatial dimension. We're only going to put one of them in the x-axis, okay? And this is the speed of light, C. And it's always at a 45-degree angle on this type of, this is called a Minkowski diagram, I think. It's always 45 degrees. And you can say, well, why is it 45 degrees? Well, we make it that because this is time, this is distance. We just make, one increment. If 1 inch is 1 second on the time thing, then 1 inch is 186 miles on the distance thing. That's the way they always add up to 186,000 miles per second, 45-degree angle. Okay. Now, if you're sitting here on here and you're not moving, you're just going through time, you're going up the t-axis, right? Look at these red lines I got going across here. Those are your simultaneous lines, okay? Meaning, and they're all parallel. I know where they are because they're all parallel to my x-axis, my x prime axis, right? And you notice that that's how they all are. And that means that anything like see A and B, if I see those and there's someone else on here moving it, he's out in space like right here, but he's moving at the same velocity I am in the same direction, so it's almost like we're both standing still. We're both in the same time frame. We will always agree that those happened at the same time, all right? But what happens when you're in a different frame of reference, right? Look at this next diagram, okay? Same thing. There's T prime. That's my prime on Earth, me and you. And X prime, that's our spatial dimension, right? And again, C for the speed of light. Now, let's say he's moving at 80% the speed of light, as we said, right? This is his movement through space, CT. It's that blue line. Now, if you notice, the faster he goes to the speed of light, the more his simultaneous lines differ from ours on Earth, okay? And the way you find out his x-axis is like this. See how these two angles are the same? So look over here. If he's going 1/3 of the speed of light, his x-axis is right here. His simultaneous lines will be parallel to that as he moves through space. Up here, look at this. There's this thing. I made the angles exactly the same so that his x-axis is right here. And then I just made them parallel lines. And those parallel red lines are the simultaneous lines in his frame of reference. Now look at this. These are the Earth's frame of reference. Remember, they're all parallel. And I drew dotted lines so you can see. They don't add up with these lines, do they? When I'm on Earth and I go 1, 2 up here, this is where the guy on that's where his simultaneous things are. See how they're different, okay? Now, I want you to think about the guy in the spaceship. We know he went 10 years on Earth time, right? And there's T prime for I, x-axis prime for I. So that's us on Earth. So we know the guy went on a spaceship for 10 years, right? We know that. He came back, there's the 10 years. We know that at the 5-year point, he turned around. So there's his turnaround. This blue line, we know that he went 80% the speed of light. And that's where that is, because there's 100%. There's 80%. So we pivot it back, and we give it the same angle. Like this angle and this angle is the same, right? Because we know he's going the same speed back as he came, as he left. Okay? We've got our angles equaling the same. Just like this angle and this angle equal the same. Now, look at the simultaneous lines. I drew them parallel to this, right? So when he gets to the halfway point, right, our lines go parallel to this, right? So there's 5 years, like we predicted. But look at him. He's only gone 3 years. See how his simultaneous lines? It's only been 3 years for him, right? Then when he turns around, again, his lines go this way because of his frame of reference just switched around, okay? And if you'll notice, how do you know that these are right? Because look at this angle right here, and I drew it in black up here. It's between the X prime and the his travel, the spaceship's traveling through space. That angle right there is 45 degrees, just like this one is 45 degrees for light. Remember, light always has to be 45 degrees if it's going to go the same speed, right? It has to go the same speed in every reference. So, and like right here, see, this is 45. Boom, 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 boom. That is a 45-degree angle. It might not be because I just drew it by hand. I didn't really get a protractor out or whatever, but it should be 45 degrees if it's going to be totally correct. All right. Now, I want you to think about that. So, we know he took 10 years. Look how long this guy took. He took 1, 2, 3. Now, look at this. This point right here is the same. He simultaneously skipped. He went boop, boop. See how these 3 points are the same exact points. Then he goes 1, 2, 3 years. This is the same point as this. 4, 5, 6 years. Remember we said he's got 6 years or 4/5 of 10. Or six, I'm sorry, not 4/5. 60%. 60% of 10 years is 6 years. And that's how long he took it. You can say, well, what the heck is this? Okay, now we're not taking into account acceleration, all right? Acceleration really plays a big key part in time dilation, a lot bigger than velocity differential. So basically, if he was turning around, not instantaneously, but in real life, this would curve around, you know what I mean? It would put it all together, like it would all mesh together, all right? But we're not doing acceleration in this because that just complicates it up. Okay. Remember up here on here, we got A and B. Let's say 2 things explode at the same exact time. Now, anyone that has the same simultaneous lines, meaning they're moving stationary, say they're moving the same exact way Earth is, but they're not on Earth. They move through space here on the x-axis to right here. Well, as long as they're going the same speed, same direction, they're going to have the same simultaneous lines, and both people will agree that when A and B exploded, they exploded at the same exact time. Okay. But what about people that are in a different frame of reference? I want you to look back at this chart here, or whatever, diagram. Look at his simultaneous lines. I got an A and a B. They explode at the same exact time according to the X prime axis, which is Earth. See, A and B. See the dotted line? They happen simultaneously in his frame of reference, you know, our frame of reference of Earth. But what about the guy on the spaceship? Now, he's moving. Now, remember, his X axis or simultaneous line is right here. Right? See the red lines, how they're all parallel? Oh, look, he goes through A, but he has another line I didn't draw it, but look at that. It would be B would actually happen a long time before A happened. And then on his direction home, look, now, according to him in the spaceship, A explodes long before B explodes. So not everything happens at the same time for everyone. Both those things are valid. It did on this one right here. A did explode. I mean, B did explode before A. And up here, A did explode before B, but only in his frame of reference is that true. In your frame of reference, they happen simultaneous. A and B, same time. Earth. You can see I drew the triangle part over here, so because it's cluttered up here. But anyways, my point is um, when the Earth guy is looking at this is the Earth guy. When he's looking at the spaceship guy, okay, through say a telescope, the light actually takes some time to get there, okay. So let's say after a year, the spaceship guy, right, he sends a picture off. It takes a while for that picture to get to the Earth guy, okay, and so after 3 years, right, the Earth guy sees him being 3 years old because it took that long for the picture to get there. You know what I mean? For the light to get to him. Okay. And the first, this is like 9 years right here for the guy on Earth. So the first 9 years he sees this the guy on the spaceship are at age 3 years. Then the last year, if you think about it, when the spaceship turns around, as he sends a picture, he's going to be going as fast as that picture almost. And when he gets to Earth, those pictures are going to basically come, you know, second by second. They're going to be cluttered up on top of each other. You know what I mean? Because he's moving along with the pictures that he sent, you know, along with the light that's, you know what I mean? So the last year of the Earth guy, he sees him age 3 years. But the space guy, right, he sees after 1 year, because after 1 year, the Earth guy takes a picture, sends it out. It takes all the way till he gets to the halfway point. If you think about it, The space guy, remember we said it's going to take him 5 years, 5 years to get to the closest star at 80% speed of light, okay? So the space contracted so that he could get there in 3 years, right? So we know that point right there is 3 years. But from the Earth's point of view, this is simultaneous from right here. That's 5 years for the Earth. See right here, 5 years. So it takes the spaceman, according to Earth's frame of reference, it takes him 5 years to get to that star. But it also takes 4 years for any light to get there, a picture or whatever. It's going to take 4 years. So when the spaceship gets there after his 3 years and Earth's 5 years, he can look at the picture finally that was sent by Earth 4 years ago. So when he gets to that planet or that star, he's getting a picture that's a year old. And look at this diagram over here. He is. These are 45-degree angles, just like these are 45-degree angles, because that's what light travels at. Remember, 45-degree angles on these graphs. So anyways, after the 3-year mission, right, he gets a picture finally of the guy on Earth, and he's only a year old, so he looks like he's younger. And then the next 3 years of his perception, his frame of reference, he sees the guy age on Earth 9 years. So he sees him age 10 years total, okay? And that's basically why. You can see from the graphs, you know what I mean, about how it takes time for the person. So when they come, so when the guy is leaving, the spaceship is leaving from Earth, all the pictures are delayed. But when he turns around, he's coming towards Earth, everything gets compressed because he's trying to catch up with those light waves.